Hello everyone, I'm Tim Hegeman and I'm a PhD student at the Vrije Universiteit Amsterdam. Today I want to share with you GradeML, our effort towards holistic performance analysis for machine learning workflows. Now, I'm sure that you're aware that machine learning has many applications in our digital society. Machine learning has enabled breakthroughs in many domains, including healthcare, science, and e-commerce. As these machine learning applications are maturing and becoming increasingly more sophisticated and widespread, the state of practice in machine learning is shifting away from ad hoc setups to train and use single models, and shifting towards more complex workflows that include many steps beyond just model training. For example, a machine learning workflow like the one depicted on this slide can include data transformation, cleaning, and validation, as well as model training, selection, compression, deployment, and inference. In the past few years, many workflow systems for machine learning have been proposed. These systems allow for easy integration and automation of machine learning applications. However, to support the growing number of machine learning workflows, we need our systems to not only be feature-rich and easy to use, but also fast and efficient in their execution. Key to creating such fast and efficient systems is understanding how existing systems perform. Of course, our interest in machine learning performance is not new. A number of approaches already exist to analyze the performance of machine learning tasks. However, these existing approaches have several key limitations for understanding the performance of machine learning workflows in particular. Most critically, existing approaches target individual steps, in particular training and inference. Now, of course, state-of-the-art performance analysis can definitely be helpful in understanding the inefficiencies in our GPU codes or in identifying, algorithmic improvements that we should be making in our training. However, when we are studying the performance of machine learning workflows, we also need the bigger picture. So which steps in our workflow are really time-consuming? And how should we allocate our resources to the different steps in our workflow? But even if we wanted to use these existing approaches, we found that most of the state-of-the-art is not readily available. So there's no source code, or the source code is not easy to deploy. We've also found that for the approaches that are available, they typically come with high overheads. For example, we looked at the built-in tracing tools for PyTorch. The figure on screen depicts the memory consumption over time of PyTorch during a training task. The colored curves represent different configurations of the tracing tool, from no tracing at the bottom in blue to full tracing at the top in red. Even for a simple training task, we found that tracing can slow down our application by nearly 10-fold and increase the memory consumption by over 100 times. These limitations leave us with a major challenge. How can we analyze the performance of machine learning workflows? We've identified four main challenges in analyzing the performance of machine learning workflows. First, how do we obtain a holistic view of the execution of a workflow? A typical workflow uses several different data processing frameworks for different steps, each with their own execution model and performance characteristics. A holistic view is needed to reason about the collective performance of different workflow steps, instead of analyzing the performance of each step in isolation. Second, how can we collect performance data with low overhead? For any performance analysis tool to be useful in a production setting, the overhead caused by data collection must be minimal. So the 10-fold slowdown that we saw with PyTorch is, for example, not acceptable in such an environment. Third, machine learning workflows are typically defined at the high level, stringing together different operations to clean data, train a model, and so on. However, performance data can cover a spectrum from workflow level metrics like how long does a workflow step take, or what's the main span of our workflow, to system level metrics, like what was the CPU utilization on machine A at timestamp T, and so on. This raises the challenge of deriving insight into performance at a high level from the varied data that we collect. And finally, how can we integrate our performance analysis tool with existing workflow systems without requiring users to complete a complex setup and configuration process? We don't expect a typical user to be experts in deploying their own data processing frameworks, so somehow we need to integrate with what's already there. So in this work, we propose a vision for holistic performance analysis for machine learning workflows. The goal of this work is to design and build a performance analysis framework that can be used to answer queries about machine learning workflow performance. For example, which steps in the workflow have the biggest impact on end-to-end performance? Or how would increasing the resource allocation of one framework impact performance? Are we using our resources efficiently during the execution of a workflow? Is my data pre-processing step bottlenecked on data transfers or computation? Or am I using my GPUs efficiently while training? And so on. So what does this vision then look like? We have synthesized 4 design pillars matching the 4 challenges I presented earlier. For each of these pillars, we have identified various sub-challenges in their design and implementation. In the next few minutes, I will introduce the 4 pillars and discuss some of the challenges, but you can find more details in our paper. Starting from the architecture of an exemplary machine learning workflow, first, we propose a unified execution model to obtain a holistic view of a workflow's execution. Such a model describes which operations make up a machine learning workflow and captures when different operations take place, in what order, and so on. More details on the unified execution model in a moment. The second pillar of our vision is a lightweight monitoring tool that collects execution traces from the machine learning system. These traces include resource utilization metrics for GPUs, CPUs, network, and so on, but also framework-specific log files and metrics, like how many data samples TensorFlow processed in a given second. The unified execution model and the execution traces are combined in a central component for data aggregation and presentation. This component correlates performance metrics for a given moment in time with the operations that we're executing at that time according to the execution model. This can reveal low-level bottlenecks, like is a particular task inside my Spark job compute or network bound, but also high-level details like is my TensorFlow job using my GPUs efficiently over time. Finally, integration in existing ML systems is defined as an orthogonal concern, so it has to be considered in the design of each component. For example, the unified execution model is derived by using existing APIs in these data processing frameworks to export information about the tasks that these frameworks are running. And execution traces are collected as much as possible using black box approaches or dynamically injecting instrumentation so that we don't need custom builds of each of these frameworks to collect the information we need. Getting back to the unified execution model, this model should represent the complete execution of a workflow. But how do we define such a model? Well, our insight was that many of the data processing frameworks used in machine learning workflows are based on data flow graphs. Think of Spark, TensorFlow, and so on. So our approach is to define this unified execution model as a hierarchical data flow graph. What does that look like? Well, we might represent our workflow, for example, as a sequence of 4 steps: data ingestion, pre-processing, model training, and deployment. And we might expand the pre-processing step by defining it as a sequence of parsing, feature extraction, and writing results. In turn, feature extraction might consist of a bunch of different tasks, all with their own dependencies, encoded inside a Spark job. Model training might be defined as a loop of training and validation substeps. And in turn, training inside a distributed setting could consist of a sequence of load steps distributed across our cluster, followed by local computation, and finally synchronization across all of these different machines in our TensorFlow system. So by defining our execution model using this hierarchical approach, we have a uniform way to query both workflow level performance by looking at the nodes at the top of our model and framework level performance by diving deeper into specific nodes. As ongoing work, we are designing and implementing a performance analysis tool called GradeML that will realize our vision. We are building on top of Grade 10, which was our earlier work on analyzing graph processing performance. In Grade 10, we already demonstrated the feasibility of this data aggregation step, combining an execution model with low-level execution traces. And we're looking to extend this towards machine learning workflows by considering workflow DAGs and so on. So in summary, machine learning is moving towards workflows, so performance analysis should focus on workflows, not just training or inference. We envision GradeML, a holistic performance analysis tool for machine learning workflows, which includes a unified execution model, low overhead trace collection, high-level insights into performance, and integration with existing systems. Thanks very much for watching.